Next up, we have Dr. Project Scientist himself, Tony Colaprete, who will be talking to us about the Volatiles Investigating Polar Exploration Rover, Viper mission, measurement goals, and traverse planning. So Tony, over to you whenever you're ready.
Okay, can you hear me?
Yep, loud and clear, and
Excellent.
we can see your slides in...
I will go to the first slide and go to slideshow. I'll try to reduce this thing out of the way.
All right, looks good.
Excellent, thanks. And yeah, good introduction to this, Dan. Well, I'll try to focus on is the measurement requirements, the measurement kind of plans, what we intend to do, a little bit more on the instruments and the traversing. Kind of fill in some of the extra details of the mission from a science perspective. Viper really has two basic science objectives, and these are pulled directly from the mission science level 1 requirements document preamble. And it's really to do two things. One is to characterize the physical distribution and state of polar water and volatiles. To understand its distribution, the cold traps and regolith, but also to work towards understanding the origin of these volatiles. This is much more of a science-driven goal compared to the next goal, which is understanding or providing the data necessary to evaluate a suite of ISRU architectures. And this is an ongoing activity within NASA and the commercial sector as to exactly what resources are at the poles of the moon and how might we utilize them. There's a range of different architectures one could choose from and work toward. And Viper is trying to provide some critical additional data to help those technology development efforts. Diving a little bit more into then what it is that Viper is going to do, and I know a lot of you have probably seen this before. It really is all about characterizing the distribution and the physical state of the volatiles at the poles. And many of you have probably seen this figure to the right. It comes from a standard used in terrestrial mineral reserve exploration by various entities, and it describes the process from going from inferred resources to a proven reserve. And we're really talking about working on the left-hand side of this, as we've obviously, as you all know, have very strong indications that there's volatiles and a range of forms, states, and distributions. So we need to increase our understanding and confidence in how they're distributed, so we can assess the probability of a reserve being available. And so to do that, there's really some critical observations that are needed, and they're highlighted here on the left. First, the distribution. We've said that. The concentration, including the lateral and vertical extent and variability. That's important. What I call the physical state. So is it ice? Is it bound? Is it chemically bound? Is it adsorbed? Is it mixed uniformly or chunky or what? So it's something about the physical state of the volatiles as well. And also, and just as important, the context and correlation of those two factors with the environment. As I'll mention in a second, it's not enough to measure the concentration in one place or another without having any ability to correlate it with broader environmental factors. And this is how, of course, we do it on Earth. When we go looking for minerals, resources, we need to do the same thing on the moon. So that includes everything from accessibility, what's the overburden, the environment, sun shadow fraction, et cetera. So these are all very important things we need to measure to really help us understand this side of this figure. So it's a distribution, physical state, context, and correlation. And the level 1 requirements are shown here. These are our full level 1 full success requirements. There aren't many, which is very much intended to be. So I'm not going to go into the details here. They're displayed. You can read them, play back and pause. But they align exactly to what I just described. The first one has to do with the distribution and the physical state. Likewise, the second, the distribution in the vertical sense. And then the next two are really correlation and context, where it's like, okay, you're going to measure these things, and this is the kind of regions you need to measure them across, and also the other things you need to pay attention to while you're measuring the volatile concentrations. So these are our level 1 requirements that drive all of the mission level 2 and measurement plans. So an important thing to keep in mind is that Viper, at its inception, going back to Resource Prospector and before that, is really borrowing heavily from what we do on Earth to develop resource models. It is really an applied science we are conducting here, not just a basic science discovery type science. It is really applying what we know in terms of processes and techniques from resource identification on Earth to the moon. So it's kind of one of the real focused efforts ever to do this on a planetary body, I believe. And what we wanted to ultimately come out with from all this is a sense of the distribution and the ability to build what we call a resource model. So on Earth, terrestrial mining companies often build what we call mineral models. They allow you to predict the distribution of a mineral type and the likelihood and the confidence that you'll find it. And that's what they take to the bank to get the money to build the mine. We certainly want to do that on the moon, but we got a whole lot of data gaps that we have to fill to do that first before we go to the bank, so to speak. And part of that is not just making the measurements, but it's also building models in terms of the emplacement and retention. And this is the applied science aspect. It's just not prospecting and trying to get lucky. It's actually thinking about where you might find water, what's the likelihood, and testing those theories then with proper exploration techniques. So ultimately, as I mentioned, we'll have a resource model that comes out of this. There's already resource models being built. Kevin had one published recently, was really nice. And that's what's going to feed into all these things here. Dan mentioned this, so I won't spend too long on this. The correlation is important. And one thing we think important to correlate to is temperature. So we're trying to make our measurements in a systematic way such that we can correlate them with some kind of spatial proxy that we can measure from orbit. So for example, temperature at the surface, but also ice stability, temperature at depth. And this is what Dan described. This is an ice stability depth map that Matt Siegler has run for us at 20-meter resolution. We organize it into those 4 temperature proxies that Dan mentioned: dry, deep, shallow, and surface. And you can see that aligned here. This allows us to actually build up a organized campaign for making measurements and making sure we make them in a systematic way so we can build these larger regional maps. Within each one of these stability regions, which we call an ice stability region, ISR, we need to characterize it at scales that are really important. And I won't get into it here, I have in the past, but impact gardening, temperature variations at very small scales are likely to be very important to controlling the distribution of water in any one of these ice stability regions. So within each one of these, we need to measure the heterogeneity across it. And by that, I mean measuring at scales less than 5 meters. We need to understand how things vary within an ice stability region. We also need to make sufficient measurements that we can characterize the total yield of an ISR. So, while a single lander or two might measure individual patches, it may not have enough continuous measurements of an area to assess a larger area or volume. And then finally, we need to compare one ISR to another ISR. Thanks. Separated by some distance. So that's all key and has to happen in one of these ISRs. So all this boils down to this set of kind of high level 2, I would call them measurement requirements. And I won't run through them all here. I'll leave it here and you guys can look at it back. But what's key is Viper is all about getting distance or odometry, a distance on the wheels. We need to cover a lot of area to actually get the kind of measurements we need to understand the distribution in each one of these ISR areas. This is the Viper mission. Dan mentioned that, so I won't go into that. A little bit more on the instruments. Dan mentioned each of these. I won't go into any more detail here except to mention to Pam's question a bit. The near-infrared spectrometer also includes a 4-channel thermal radiometer, as Bethany described. it's really nice to have a simultaneous measurement of the infrared temperature as well as the near-infrared spectra, which goes out to 4 microns on this spectrometer as well. But I also will mention that we have a great set of navigation and hazard cameras that are going to provide fantastic geologic context, wonderful imagery, and also, of course, lights. We go into places, the illumination conditions at the poles are incredibly challenging and exciting. And so we really are developing some systems here to rove and maneuver within these shadowed regions, both in shadow, between shadows, and that's all going to provide excellent scientific data. We are also, of course, capturing all the other rover sensors for science, everything from motor currents to temperatures, et cetera, that can be used for science. Real quick, prospecting is when we're driving. All the instruments are on except the drill, of course, while driving. And this is a fundamental difference from a resource prospector as well. We have the near-infrared spectrometer, the mass spectrometer, always looking under the rover, and the neutron spectrometer constantly measuring neutrons flux. We have constant measurement of surface temperatures as well from under the rover. So in this way, we can really build the density, the aerial density needed to actually get the uncertainties down in terms of total water concentration in an area. When we do drill, as Dan mentioned, we have a 1 meter drill. It goes down and brings up samples in 10 centimeter bites, we call them, just 10 centimeter sections. Each section is observed simultaneously with the M-SOLA, which is the mass spectrometer, and the near-infrared spectrometer fields of view. This gives us both the solid and the gaseous concentrations of a wide range of species. All these requirements I've described go into a range of science operation plans and documents, and this gets very detailed. I won't get into it in detail here, but this is just an example of some of the science activities that have to be built and then brought into a traverse planning tool, which is a very complex problem when you have both sun and COM constantly moving dynamically, you have slopes and everything else. But this is all being done now to build a series of traverses to evaluate both the rover design and the science operations. And this is one of my last slides here, is just an example of a Viper study traverse. This is a South Pole area north from the crater Nobile. This shows this white line is a traverse. Each one is approximately 1 lunar day. And we're running out to these red areas, which are PSR, ice stability regions. The green and yellow are the other ice stability regions of shallow and deep. And we run out there and conduct a range of science activities at what we call science stations. And this gives some of the statistics here in terms of total amount of measurements and whatnot. One thing I'll point out is this is overlaid on top of a 1 meter DEM from NAC images. So it's not stereo, it's made from shading. And it allows you to get actually fantastic NAC D at much higher posting. And with that, this is my last slide here. So we've all seen the fantastic discovery that's been made over the last decade. And we're finally getting back to the surface with a range of missions, Viper being one of several that really, I think, provides the next steps in our exploration and documenting of the resources potentially at the South Pole of the Moon. And with that, thank you.
All right, thanks, Tony. Great talk, and I see you have 4 questions in the chat window. In the interest of time, I'm gonna let you take a look at those in the chat when you get a chance, and otherwise we'll defer them towards the end.